Hi, thank you for joining us for a podcast by Metrum Research Group. I'm Heidi Seaborg. In today's podcast, our science team has selected a paper they've recognized to be influential for MetrumRG and more broadly for the pharmacometrics community. I'm joined today by Jim Rogers, our VP of Statistics. Jim has been with Metrum Research Group for over 15 years. He is as adept with prose as he is with numbers. And for today's podcast, he has selected the paper Bayesian Workflow. This paper was published open access in 2020, and we will post a link to this article along with this podcast. Joining Jim in today's discussion are co-authors of Bayesian Workflow, Andrew Gelman and Charles Margossian. Andrew Gelman is a professor of statistics and political science at Columbia University, and he likely needs little introduction to listeners on a topic of Bayesian statistics. Charles Margossian is a research fellow at the Flatiron Institute in New York. He is also a friend of Metrum Research Group, having completed a stint as a visiting scientist here at the company prior to receiving his PhD in statistics under Professor Gelman. So now I'm going to hand things off to Jim, who will moderate today's discussion. Thanks, Jim.
All right. Thank you very much, Heidi. And thank you very much, Professor Gelman and Charles Margossian, for joining us today and for talking to me about this paper that, for reasons that will become apparent, were kind of special interest to me and to my colleagues at Metrum. I think anyone who has clicked on the link probably has some conception of Bayesian analysis, but the term workflow is not so much in common parlance yet in statistics. Let me just put it to each of you to paint a picture. It doesn't need to be a precise definition, but paint a picture of what you're trying to get at when you refer to workflow. Dr. Gelman, let me start with you.
So we can talk, maybe Charles can talk about like what he feels Bayesian workflow is, but just workflow in general. I have this idea that there's a spectrum in what we do in statistics, and we start with examples, and then the more abstract version of that is a case study where you take an example and you kind of try to abstract what methods you're doing and how you're doing that. The next step is a workflow, which is a set of steps which would apply more generally. Then comes a method, which is a bit more codified, and finally there would be a theory that would have some mathematical formulation. So I think of workflow as kind of being in the middle, and I think that in statistics and maybe in engineering in general, we spend a lot of time talking about theory and a lot of time talking about examples and not enough in these intermediate steps. And I felt that there were a lot of things that were good statistical practice, good Bayesian practice, which had not made it into Bayesian theory. It had not made it into our Bayesian data analysis book, which is basically methods with some theory. And it seemed that it would be useful to try to express this, to try to make it a workflow, not just a bunch of case studies, even if it hasn't quite reached the full level of maturity that might be called a method or a theory.
Great. Charles, anything you want to add to that?
Yeah, maybe I'll make a description of the workflow that's a bit orthogonal and complementary to what Andrew says. The way I see it is that it's trying to take a more holistic approach to data analysis. And you look at the different components of the workflow. So one of them is model fitting. And I think that's often what's emphasized in statistics. When you take a course in statistics, when you look at the theory of statistics, when you look at the methods that are being developed. But actually, when you work on an applied problem, you do much more than fit a single model. You're actually developing the model, you're criticizing the model, you're revising the model, you're doing model comparisons. And there are some important lessons, when we think about the methods we're developing and the algorithms we're developing. If I'm only fitting a single model, I can try and build a very specialized method that's going to work specifically for this model. If, on the other hand, I'm aware that my data analysis is going to involve working through multiple models, suddenly I need my inference algorithms, I need my software to work seamlessly across many models. And that's the workflow perspective. And if I think about the software development that we do, so for example, with the STAN team, that we've all been very involved, both at Columbia University, at the Flatiron Institute, and also at Metrum Research Group, right? That kind of software and probabilistic framework is really intended to support the workflow in a comprehensive manner. And one of the goals of this paper is to clarify, look, those are the requisites for developing a probabilistic framework that is going to be useful to applied statisticians.
Yeah. Okay. So I want to pick up on the connection that you both mentioned between applied statisticians and theoretical statisticians, or more methodologically focused statisticians. There's a great graphic in your paper, figure 2, and you described this in words, Andrew, going from example to theory. And I think we'll come back to this later, but one of the things that we really appreciate about it at Metrum, we're essentially applied statisticians and applied modelers, and that it's finding this middle place here that requires a lot of effort and thought that doesn't get talked about a lot or hasn't in the past, called workflow, that's really forming a connection in a sense to the theory. Charles, I want to, before we go any further too, we were talking about this before we started recording. From your time at Metrum, you know that we're big fans of Bayesian approaches, especially in pharmacometrics. That's been a big deal for us. But we also fit a lot of models just with maximum likelihood. We're sort of promiscuous modelers, maybe you could say. And what struck me as I was reading the paper is the vast majority of it, just suggest, is applicable whether one is Bayesian or not. If you're fitting any sort of complex model, most of this will apply. Maybe not the stuff on priors and not the particularities of sampling convergence and stuff. But would you agree with that, or what's your take on that?
Yes, I absolutely agree with that. And I think that, to the extent that we think of priors as part of the model, this idea of, model checking, model validation, that applies broadly across statistics and machine learning. So maybe there is a sense, and Andrew, I'm curious to hear your opinion on this, that we could have called this the data analysis or data science workflow rather than the Bayesian workflow. What I can think is, will the examples and the motivations that we're very familiar with come from Bayesian modeling? But I wonder if there's a case to be made for renaming the paper to something a bit more general.
Well, whether we should rename the paper, I think if you were to say data science workflow, there would be a lot more focus on handling the data itself, which is important also. Here, I think we are doing probability modeling is kind of central. There's an annoying thing that Bayesians do, which is they take a non-Bayesian approach and they say, well, that's actually Bayesian under this model. And this is an old annoying thing that Bayesians have done. Gauss annoyingly took least squares or invented least squares and said, well, this fits with the Gaussian distribution, and Laplace did similar things. I think there's value in it. Now, as the statistician John Tukey wrote, you should be able to evaluate a method on its own. That is, Tukey would think of the probability model as the scaffolding that's used to construct the method, and then he would kick the scaffolding away and say, if you want to use least squares, you should use it because you think it works well, not because you have a derivation based on a model that you don't believe. So you can kind of take that, there's kind of different ways of looking at it. I think the value of the annoying Bayesian approach, if the anti-value of it is kind of what Tukey warns about, which is taking your model too seriously. But the value of it is that it can, if you have a method that would seem to fit a Bayesian approach, but then aspects of the method violate it, then there might be ways of improving. For example, decision analysis using statistical significance, you should be able to do better, and companies can do better by doing a more formal decision analytic framework. There are some classic problems in statistics, which if you think about them from a decision analytic or Bayesian point of view, kind of crumble. So one of them is the problem of estimating a ratio of two parameters, which in classical statistics is called the Feiler-Creasy problem, and it's well known, be very difficult to attain a confidence interval for a ratio of two parameters. The difficulty entirely comes when the denominator is of uncertain sign. But if you have a ratio of A over B and B is of uncertain sign, the meaning of A and B, of A over B changes when the sign of B changes. For example, an example such as marginal cost benefit ratios or ratios of regression coefficients in general. So that ratio is one of these things that's a mathematical statement, but it's not the answer to any particular question. So that's an example of how, and this is not discussed in an article or even really very much in our Bayesian data analysis book, but this is a way, and this is an example of how using math, Bayesian analysis, can give you statistical insight. And I wanted to mention that partly because there is a tendency when we talk about this stuff to frame ourselves as the applied people. Like, we're the reasonable people. We're not those jackasses proving theorems. Like, we care. You know, we're applied. We're good, blah, 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 blah. Well, that's silly. I mean, we get a lot. Workflows right there in the middle. And one of the purposes of this paper and this research, this line of endeavor, is to bring various technical theoretical ideas into the applied world. So people like Tamara Broderick and others have been working on methods of evaluating influence and sensitivity, and they prove a lot of theorems. Now, I want to do stuff like, hey, I just fit a multi-compartment model, and it turns out that with the data I have, I can get very precise estimates for certain compartments where the concentration decays over a period of several days, but other compartments that have where the concentration drops very quickly, I can't estimate that well. And why is that? Well, I should be able to map that to the data and say, well, the first compartment's being estimated by this whole range of data. The second compartment is really only effectively estimated by data in a very narrow range. So I should want to create a graph of some sort where if I were to isolate a particular parameter and then say which data points supply more information, well, to do that, I will want to bring in some of those theoretical tools, these methods and theories that have been developed. But for this purpose of understanding a model, and the goal of understanding is something we do all the time. It's like, you can get so much. I always say this, to be a good scientist, it's the capability of being upset by things is very important. So we should be upset that when we talk about stuff, we're spending a lot of time saying, well, this model didn't quite make sense because of blah, 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 or we needed to do this because otherwise, blah, blah, blah. Then you look in the textbook and there's no statement of that. There are no methods for handling that. So we'd like to bridge that gap. But the bridging that gap is not merely, oh, hey, we know what we do, we know what we're doing, and we're trying to spread it to the world. A lot of that is to make use of the existing and in development theoretical ideas.
Yeah. Yeah, it's interesting. I had written, actually, I was going to thank you and your co-authors for writing what I sort of considered an ode to applied modelers, but it's more than that. It's talking about the collaboration between applied modelers and methodologists, and really I don't know if you talk about it quite this way, but the workflow itself is something that's crying out for method. It's crying out for a principled approach.
And there is some of that in engineering. So the term workflow, it's kind of been in the air. We have some citations of it being used in Bayesian statistics by Jim Savage, I think was the first one, and some predecessors. But I think in engineering, in particular software engineering, there's been a lot of talk about workflow. And I think that's why we and others started talking about it, was we must have been hearing that phrase used. And they are trying to do that.
Yeah.
I mean, there's definitely I think there can be sometimes an apparent disconnect between application and theory. So, how do we bridge that? And how do we, connect the application to the methodology, to the theory, right? That's one attempt. And there also, I agree with Andrew that there are different levels of how principled we can be. So Jim, you use the word principle. So what does it mean to do things in a principled way? You can also ask, what does it mean to do things in an optimal way? I'll mention another paper that Andrew and I wrote, which is actually a chapter for an upcoming textbook, which was for how many iterations should we run MCMC, right? So that's the kind of question that is very practical, right? So anyone who is going to use MCMC is going to have to contend with that question unless they decide to simply rely on software defaults. But if they do that, they might not get adequate results, or they might use too much computation or not enough computation. And I think there is a level at which we want to come up with a principled answer to that. On the one hand, we have experience fitting a lot of models, running MCMC, and we can formalize that a little bit into empirical evidence. We also have methods which I think are theoretically well motivated. So something like a convergence diagnostic, like RHAT or some of its variants, we can actually, develop some theory to motivate what we're doing, that we can demonstrate sometimes analytically on some examples that it really does what we want it to do. And then maybe there's even another level, which is, well, can we get theoretical guarantees that it's always going to work, and that it's, and usually those theoretical guarantees, they're you're not going to get them for a lot of the problems that we're interested in, but you can get them in specific cases, and then those specific cases give you insights into a broader class of cases. So then, that also becomes theoretical motivation, right? And then that becomes heuristics and principal applications of methods. So I think that we are really trying to think at all these different levels without being afraid, to try a method, even if the conditions under which we apply this method maybe don't enjoy all the theoretical guarantees that we would want it to have. Or maybe we start to rely on theoretical motivation, or maybe there are some gaps in how to make this principle, right? And this question of how long should Markov chains be, I think that's a prime example of, it sounds like this should be a tutorial rather than a research topic. And it is both, right?
Yeah. And one of the things I've been really happy to see as you kind of moved on from Metrum, Charles, is that you haven't lost touch with those very practical questions of things like, how many iterations do I need? And I've seen you put out a lot of great work on that since you left us. Let me jump to give people a more concrete sense of what we're talking about. Let me jump into one of the examples in your paper. And Charles, I'm going to have to beg your forgiveness here. I didn't pick the interplanetary motion example. I know that had your fingerprints all over it, but that's a slightly more complicated example to talk about. I would recommend it to anyone who has found themselves in a situation of not getting convergence of their model, or not even, maybe the sampler is going too slow that you don't even know if you're going to get convergence. That type of problem, it's a very good example to illustrate that. But I want to focus on a simpler example.
Maybe go ahead. One comment I will say about that example is, so Andrew gave me that example as, I need a simple example for a class that I'm teaching. Can you quickly fit a model and get the results? And it turns out you can't quickly fit a model, get the results, and there was some unexpected complications. But yes, anyways, I agree that the golf example is frankly also the example I prefer in the paper.
That's saying something. For those who don't know, is it fair to say your first love was sort of astrophysics, and we've gradually pulled you into the sphere of statistics? I don't know if that's a fair.
I studied physics in college too.
Okay, so kindred spirits. All right, that's actually very related to the type of question I wanted to ask about the golf example. And let me share my screen here to give people a sense. If for those who don't have the video, just listening on audio, and there's a figure in the paper, figure 26. It's describing sort of the geometry of golf putting and showing how basically the further away you are from the hole, the more precise you need to be in terms of the angle that you hit the ball. And so that basic principle from Euclidean geometry, not principle, the result of Euclidean geometry is not initially, but eventually is baked into the modeling strategy here. It's the sort of motivation that a lot of folks in the pharmacometrics world, I think, will really resonate, because it's sort of, I don't know if you'd call it a mechanistic motivation here, but it's any of these things that are from first principles. I think a lot of us would prefer a model that, as much as possible, is relying on first principles or mechanism, both because it leads to better explanatory power and better ability to extrapolate, do causal inference, and so forth. So there's a lot of that in here. Then there is also, however, and I'll just stop sharing my screen and speak to it. At one point, you find that you augment the data set, and then you end up with the model being very influenced by, this is related to what you were saying earlier about the compartmental example. The model being more pulled by the data in one area. You end up problems with sort of like binomial over dispersion. And the way to, the decision that is made about how to deal with that, you literally call it a fudge factor. So it's a very empirical, kind of practical approach. And I think, and you tell me if I'm reading too much into this, there would be a very natural and understandable kind of hesitancy a lot of times to just throw in empirical fudge factors. In fact, we could probably have a good detour here, Charles, about Einstein throwing in gravitational constants. So the willingness to just try that, I guess. What I'm reading into it is the willingness to try that. Maybe you're more open to it if you're operating in a frame of mind that's a very learning-oriented framework. And maybe I'll just briefly share this other figure, the very first figure in the paper, where you show that you're iterating through a whole series of models and navigating this whole space. And these models are going to be sort of mutually informative with respect to each other. So this amounts, we're not going to try to process this whole diagram, but this amounts to navigating through an entire model space. And when those models when you're letting them be in dialogue with each other, rather than just looking for a sort of hero model that's going to carry the day on its own, that's what it seems to me, that's a big part of what workflow is getting at, is putting multiple models in dialogue with each other. So my question to both of you is that a fair characterization? Why is that important? What are key areas where we need multiple models and not just one? Kind of open-ended question. I'll leave it to the two of you to decide who wants to comment on that.
Okay, so there are a lot of reasons. Okay, one thing is, let's suppose you're fitting a 4-compartment model. Probably want to fit a 3-compartment model just to show that that wasn't enough. And then you want to fit a 5-compartment model to show that you didn't need it. So that's
That'd be a great bumper sticker.
and then now beyond that, you can say that we're like doing this sort of workflow with multiple models is a way of trying to, as an individual scientist or as a small team, trying to somehow create the conditions of the larger scientific enterprise. So when I fit more than one model, that's kind of easier than me fitting one model and writing a paper and someone else fitting another model and so forth. So there's no reason we need to be limited to that. Now, as often is the case in statistics, existing theory is a little bit narrow. So typical theory is about choosing the best model or doing model averaging, and we've written about that too. But here, fitting multiple models in order to understand the process is something different. It's useful for it to be formalized. So one of our goals of putting this into workflow. So yeah, the golf example, that's an example where we fit a series of models. And actually, we got more models. I didn't like that fudge factors. We have a cleaner version, which is, it's in the Bayesian Workflow book, in the golf chapter, but the book is book isn't quite finished yet, but we're close. But the point is that, okay, that's an example, or maybe it's a case study. To what extent can we formalize that into workflow and say you will be fitting a series of models, and we should be able to have a kind of patterned way of talking about that.
Mm-hmm. Yeah, well, I have some thoughts and some pondering about this question. And one thing I do like a lot about pharmacometrics is we're fitting these compartment models, and we have a sense that these models are simplifications, not just of the pharmacological process that we're describing, but even of other models that we could be using. And there's this nice spectrum of complexity from compartment models to semi-mechanistic models, and then maybe physiologically based models, and then all the way to systems pharmacology models. And I know that the researchers at Metrum actually cover this spectrum of models. We're kind of at a point in Bayesian statistics where I think we do a good job up to the level of semi-mechanistic models. And then I've seen some attempts at doing PBPK models, where people already uncover some interesting complications in terms of computation, in terms of identifiability of the parameters. And then we have these systems pharmacology models, which are biologically very well motivated, but there are some serious computational challenges and there's some serious statistical challenges in fitting these models. You know, the question we need to ask is, well, what kind of models do we need to look at the data to make the science advance? And there's a sense that, you know, the more complicated model, the model that has maybe the highest fidelity to reality, is not always the model that either is going to be manageable at a very practical level, or that is going to give you the most insights in order to, you know, then make a downstream decision, such as prescribing, you know, a dosing regimen or something like that. And I am wondering, you know, what are principal ways to navigate this space of models where there are these trade-offs, these clear trade-offs in pharmacology, and it's not exactly clear how it gets resolved. And I'll give you another example of a trade-off that I worry about, and it actually comes from machine learning. And I think you'll see the connection where, you know, in machine learning, people often fit neural networks. And here, there's a very clear decision about how big do these neural networks need to be, right? What is the depth? What is the width? And if you have a big neural network, then in a way, your model can achieve higher fidelity to the process you're actually trying to describe. But then what people do is they fit these really big neural networks with inference methods that are very approximate and very poor. And so there's kind of a trade-off between the quality of the approximation of the inference and the quality of the model. And you could imagine a similar trade-off in pharmacometrics, where maybe, you know, someone is going to think, oh, I'm going to fit a systems pharmacology model. But to do that, I can't do a full Bayesian inference. I can't do an expensive inference method. If you want to think outside of Bayesian context, I'm going to use an approximate method. And then the question is, how is your computation best allocated? Is it best allocated into the model, or is it best allocated into the inference? And I think that having a way to compare models and to think through models, but not only compare models, but compare fitted models, which can include a model that is fitted with a very reliable inference method and a model that is fitted with an approximate inference method, is important to navigate this question.
Yeah, so you at least have to see these things sort of side by side in order to make an informed judgment. How approximate do you want to be, and so forth, right?
Yeah, but to be fair, I'm completely raising this as a question. I don't have a good answer or a good way to start tackling this problem. I think that, you know, I mean, people have thought about this, right? But at least in my personal journey, let's hear it. Yeah, Andrew.
Let me just mention the folk theorem of statistical computing, that if you have a problem with your computing, there's often a problem with your model. It doesn't have to be. You can have there are legitimately difficult computational problems, but quite often that's the case. And that affects our workflow in various ways. So one way it affects our workflow is just very directly when we have problems with computing, don't start throwing computing resources at it right away. Take that as a signal, as a probabilistic signal that maybe you have a problem. Take that one step back. that suggests that we should be diagnosing computing issues, not merely because we're worried about computing, but because they could reveal problems. So what if you had some super efficient computer and it could just crunch through everything? You'd still want to reveal that there had been a computing problem. From the other direction, it suggests directions that we're still working on with Stan, especially in the adaptation phase, because currently, I mean, not just with Stan, but I know this with Stan, that you can spend most of your computing time on your mistakes. It's a little bit like papers that are refereed. The best paper gets refereed 3 times and gets published. The worst paper gets refereed 15 times because it went to 5 journals before it got published. That's not completely true, but there is this weird way in which the review effort is higher for the papers that maybe shouldn't have been out there in the first place. So similarly, we run Stan and it's super slow, and it turns out there's a bad model, and we waited a long time. Often you have users who, like, we're all like this sometimes. We don't really want to think that hard. So our first reaction is to run something longer and then put off the day of reckoning. A better workflow would be that we call the fail fast workflow, which turns out that's another one that was in the software engineering literature. So I thought I had come up with this, but I must have also like taken it from something that somebody had said. We want Stan's adaptation to change. We want it the default to be you run something very quickly, and when you have problems, then you realize it right away. Currently, the default is 2,000 iterations, and then you sit there and say, well, I should have realized this problem much earlier. So that folk theorem has a lot of implications in computation as well as modeling.
Yeah. All right. Let's take a turn to, we've already started talking about some practical issues, but for those who are maybe listening and saying, okay, I get what this workflow is all about, and how do I do it better or less badly? What are the kind of important tools to use? Because it's not easy to do everything that we're talking about. That complicated diagram that I threw up without navigating the model space, keeping track of what you're doing and why you're doing it and all that sort of thing is hard work. So I want to just offer first, that's something, this is why this is such an important paper to us. We've devoted a lot of thought to that at Metrum, and we've developed our own system for doing that. And for anybody who's interested in that, we have some expos, we call them expos, that are available online, and we'll give the link to that. And it's just open source tooling and process for the way that seems best to us to do that in pharmacometrics. So that's our special kind of angle and interest. What do you both do, and what do you see on the horizon in terms of better tooling? What are the key kind of practical considerations that you'd want to call people's attention to? Charles, I see you nodding, so let's go with you first.
No, I mean, I'll tell you what I'm thinking about, which is not a direct answer to your question, but I'm now putting my hat as a Stan developer, as a Torsten developer, which is one of the hurdles for people to do some of the things we recommend, and that includes, prior predictive checks, simulation-based calibration, posterior predictive checks. There's another check that I really like and that I've discovered maybe 2-3 years ago, but now I teach it when I give a workshop on Stan, is how to check that your ODE integrator inside your model is accurate enough or not, right? And I don't think that's something people check in a typical Bayesian pharmacometrics workflow. And the reason you would want to check that is not because I think integrators by default are not precise enough, but probably because you could get away with less precision. It wouldn't change the quality of your posterior samples, but it would reduce your compute time. But it's actually difficult to implement those checks. And if I think about what's useful to practitioners, is software that gives them maybe not a completely automated way, but at least gets them some of the way to doing those checks using a function in a quick way. So a lot of the work, to making those. So I've listed now a number of checks, and the question is, do we have the software infrastructure that is going to help a pharmacometrician implement those checks implement those checks in a reproducible manner, meaning that if someone goes through their code, it's not overly complicated and they can also do it well, and then implement those checks in a systematic way. The simpler the code to implement those checks, the more you can make this systematic. And again, with the caveat that different problems are going to motivate different checks. So that's also something to be aware of. That's the first point. The second point, and again, I realize I'm keeping things a little bit at a high level, is to appreciate that different methods are amenable to different checks. So for example, I think MCMC, because of the theory that exists, because of the decades during which it has been used, now has a lot of checks that you can implement to verify the validity of the inference. Something like variational inference has less checks that you can do to make sure that your inference is doing what it's supposed to do. There is an exciting avenue of research that Paul Berkner, who is also a co-author on the Bayesian workflow, is pushing, is the so-called amortized inference. And at least from what I can tell, the computation is expensive. But once you've done the computation once, you can reuse that computation to fit the model to a new data set. So that's good if you want to do things like cross-validation, if you want to do things like simulation-based calibration. So it's kind of like, well, you pay an upfront cost on the inference, but then the computational cost of doing all these other checks, which are part of the Bayesian workflow, is smaller. And so that's an example of how the technology can lower the barrier towards doing these checks and these other components of the workflow.
Yeah. Maybe I should just mention briefly, probably most people listening would know this, but Paul Berkner is the author of BRMS, among, I guess, probably other things, but that's what I know him for. I mean, there's so much intelligence baked into that package at this point, and more, apparently more on the way. So that's certainly one promising thing. Not just promising, it's there already.
It's being developed. The research is being developed, validated, tested out. But yeah, if I think about what is one thing I would like to add to Torsten, is a very simple way to check, is my OD integrator precise enough? Mm-hmm. Can I play with a less strict tolerance to make my computation faster? But at least then I can check whether I've been too much of a maverick or not.
Yeah. Andrew, let me turn to you, and I think we should probably try to wrap up, but I'll give you a chance if you want to add anything with respect to kind of practical tooling and so forth, please do. And then I'd like you to, if you could sort of close with a claim that's made in the paper, which I think is a laudably bold claim that says, I guess I don't have the exact quote here, but it says, you see model navigation as the next transformative step in data science. So I'm certainly one who's willing to stipulate to that. But what would that entail in terms of the way that we develop the next generation of statisticians? Should we be asking them to focus on things that are a little different than what they have in the past?
Statistics has been described as the science of defaults. That's certainly true of those of us who write textbooks, or people like Paul who write software, or us who write software packages. But even if you're doing something just once, your method is somehow being justified by the idea that you're applying a general procedure. And so it is much harder to write code or develop a method that you feel comfortable sharing with people that they can run with on their own. Failing that, we do our examples and case studies, and people can try to imitate that. That's not as good, though. Having a workflow is better than having a case study, partly because people aren't always clear how to imitate. For example, I'm not so good on the computer sometimes, so if I'm trying to install some software, I follow the instructions, and I'm never completely sure. It's like a recipe. A good cook knows which steps are important and which things you can substitute out. Otherwise, it's very difficult. So that's a lot of what makes a workflow different from a series of examples. I've just seen a lot of cases in statistics of people trying to follow the template of what came before and just copying all the wrong things and missing missing.
Okay. I'll wrap up unless either of you have any closing thoughts that we didn't have a chance to get to.
I mean,
Charles, give his closing thoughts because he represents the future.
maybe an
Awesome.
opening thought then, looking forward. I'm going to try and answer your question, Jim, and maybe to take Andrew's claim a little bit further, to say, I think this is, transforming how we think about statistics, but how we think about science, which is there's this traditional framework of, a big part of statistics is to test or validate hypotheses using data. And there's this idea that the hypotheses, which is based on a model, which is a model in a lot of ways, exists in a fixed way. And that then we're gonna have to validate or invalidate it. And to be fair, that's still a big part, an important part of statistics. If I think about, again, drug development, at some point there's a clinical trial that needs to confirm that the drug is not toxic and effective. And you need that to get it approved by the FDA. But what we're thinking more about is that, well, the model is not, it's not fixed, it's not given. Like in the process of developing a model, there is a lot that needs to happen. There are a lot of different models that have to be tried. There's data that needs to be analyzed and explored. And there's that whole process where I think people are interacting much more with data than they might have once upon a time. And part of this is because there is a bigger abundance of data. I think, I see this trend in machine learning where people have this data and they really have no idea what is the process that generates an image, right? I mean, the process that generates an image is painting, right? But that's not what they're trying to emulate. And so people started having a more pragmatic approach where we're going to try and find a model that describes the data, that describes the world, as opposed to we're going to try and validate and invalidate the hypotheses. Or on our way to developing a hypothesis, we're going to interact with the data. Or if our hypothesis is invalidated, we're going to try and refine it and come up with a better one based on what we've learned from the invalidation of the data. And those are things that exist. Those are not things that replace hypothesis testing. But maybe there are things that we should pay more attention to, and that more of the statistical method and theory should concern itself with. And, when I think about that sentence that's in the Bayesian Workflow paper, that I didn't write that sentence, but that's how, I'm assuming Andrew did, and that's how I'm reacting. That's the kind of shift that I see this sentence foreshadowing.
All right. Great. Thank you. Well, that's, I think, both a practical vision for the future. I mean, it doesn't sound crazy, but it's also exciting because it is it's a different emphasis. Well, thank you both very much for your time. Really appreciated. I hope anyone listening has learned a lot in the process and enjoyed the conversation. I certainly have. Thank you.